In the previous video, I introduced you to Hooke's law, which is the basic physical principle which describes the forces exerted by a spring, which is either compressed or stretched. So I'm going to do a quick recap of Hooke's law, and then we're going to go into an example problem. So to start, let's just say we have a spring here, and the spring is at its resting length. So this spring is not compressed, it's not extended, it's just sitting there resting. Now we imagine that a hand comes in and pulls on the spring so that the spring extends through a distance delta L. So here we have the hand pulling on the spring pulling on the hand. The two forces are equally strong, and the strength of either force is given by what's known as the spring constant multiplied by the extension of the spring. On the other hand, let's say that the hand comes in and compresses the spring. So here we have that the hand has compressed the spring through a distance delta L. Now the hand is pushing the spring to the left. The spring is pushing the hand to the right. The hand and the spring exert forces on each other which are equally strong. In this case, the strength of either force is given by the spring constant multiplied by the compression of the spring. I want to emphasize that the spring constant, indicated by this constant K here, is unique for a given spring. So if I have one particular spring, we will use the same constant K to describe the compression of that spring or to describe the extension of that spring. All right, let's get to the example problem. So here I have two springs. The upper spring, which I drew in blue, is connected to the ceiling. And then down here, it is connected to spring 2. Spring 2 is connected to the floor. And then up here, it's connected to spring 1. In this initial picture here, both springs are at their resting length. So neither spring is compressed and neither spring is stretched. Both springs are at their relaxed lengths. Now what I'm going to do is come into this point where the springs are connected to each other and stick a mass in there. Once I put the mass in there, I release the system. Then gravity is going to pull down on the mass. And because gravity is pulling down on the mass, that upper spring gets stretched and the lower spring gets compressed. So now the mass is just sitting there with the upper spring extended and the lower spring compressed. We want to find this distance x between the original point where the springs are connected to each other and this point over here where both springs are connected to that mass m. When we do this problem, we're going to assume that the mass here is very small, so we don't have to worry about this mass occupying space that used to be occupied by the springs, which would then cause further compression or extension of the springs. Okay, so now let's go about finding this distance x here. And we're going to start by drawing a force diagram for the mass. So as usual, we're going to start our force diagram process by putting in a dashed line around the mass. I'll come over to the side here and draw a clean version of the mass. And what I'd invite you to do now is pause the video and draw a complete force diagram for the mass. And on that force diagram, you can draw the forces, and you can also put in expressions for the magnitudes of the forces, where here you would be using Hooke's law to write down correct expressions for the magnitudes of the forces exerted by the springs. All right. First force we would put in is the gravitational force. That would have magnitude mg. Now let's go around the dashed line. So if I start here and go around the dashed line, I can see where the upper spring is reaching in to pull upward on the mass. So I'm going to go into the figure and put in the force that spring 1 exerts on the mass. I'm going to call this Fs1. Using Hooke's law, the force exerted by that spring would be Hooke's constant multiplied by the extension of the spring. So the spring constant for the upper spring is K1. The extension of that upper spring, you can see here, is X. Now I'm going to continue around the dashed line. And down here, you can see where the lower spring is reaching in through the dashed line. And here the lower spring is going to be pushing upward on the mass. It may be a bit surprising that this lower spring is pushing upward on the mass, but let's come to this figure over here. If that spring over here starts out at rest, and I then compress that spring, the spring is going to respond by pushing back on my hand, right? So here, the presence of that mass is pushing down on the lower spring. The lower spring is going to respond by pushing upward on the mass. Okay, so I come into the force diagram here, and I'm going to put in an expression for the upward force the lower spring exerts on the mass. We're going to call that one Fs2. To find the magnitude of that force, I will use Hooke's law over here. Hooke's law applied to a compressed spring. We put, first of all, the spring constant, which is K2 for the lower spring. And then we put in the compression of the spring. And if you compare these two figures here and here, you can see that the lower spring has been compressed by a distance x. So that's what I put in here. The magnitude of the force is K2x. Okay, so now we proceed as usual. And you can see that what we're going to do next is introduce a y-axis. And at this point, I'd encourage you to go ahead and try and finish out the problem on your own. Make your grid, put in the y components of each of the forces, sum those to 0, see if you can get an answer, and then you can rejoin the video and see if your answer matches mine. All right, here we go. You have gravitational force, spring force 1, spring force 2. So for this problem, we only need y components. There's nothing going on in the x direction. All right, putting in the y components. The y component of the gravitational force is minus mg. The y component of spring force 1 is k1x. The y component of spring force 2 is k2x. Now we sum the y components of the forces to 0. So add them up. We have minus mg plus k1x plus k2x equals 0. Okay, we're solving for x. So I'm going to do two algebra steps. Take that minus mg, put it on the right where it picks up a plus sign. And then with those remaining two terms, I'll factor out the x. So I then have on the left k1 plus k2 times x. Okay, isolate the x. We have x equals mg over k1 plus k2. Now substituting the mass is 0.50 kilograms. G is 9.8 meters per second squared. Here I'm just going to put in the sum of the spring constants. 30 newtons per meter plus 20 newtons per meter would be 50 newtons per meter. Let's do the unit checking here. In the numerator, I have kilograms times meters per second squared, which is a newton. In the denominator, I have newtons per meter. Newtons cancel newtons. So then in the denominator, I have 1 over meters, but 1 over meters in the denominator becomes meters in the numerator. So we have the correct unit. So x is going to be some number of meters, as we would expect. And then if you plug into your calculator, you'll get x equals 0.098 meters. So now we have done an example problem using Hooke's law. And from here on, when we do problems involving springs, we're going to be more interested in the potential energy stored by the spring when it is either compressed or extended.